Good morning and welcome to this next lecture on vibrations of plates and shells. Last time we had ended up here where we completed the derivation for a circular plate that is clamped at the edges. Okay. So we found the U3 mnth mode shape as this function over here. Okay. Now there are two indices m and n, and it will turn out that m is indicative of the number of nodal circles and n is indicative of the number of nodal diameters. Okay. So I would like to show you a few modes animated in MATLAB. Okay. So let us go to the other monitor. So here okay. This is the M0 N0 mode. Okay. It is what we call the very first breathing mode of the plate, and you can kind of see the edge over here where displacement is 0 and also the slope is 0. Okay. You can see the slope is 0. Okay. So this is the very first mode. No nodal circles, no diametral circles, and no nodal circles, no diametral node lines. Okay. Let me close this and we will go for the next mode. Okay. Now here n is equal to 1. So you have one diametral node line. Okay. So you have this diametral node line. So it is like cos theta, cos 1 theta. Circumferentially it is cos 1 theta. Earlier one was cos 0 theta. Okay. Now the next one here is this. Okay. So now there are two diametral nodal lines. Okay. So this is n equal to 2. Let us see what the next one has. Okay, so this has m equal to 1 and n equal to 1. Okay, so this is m equal to 1 and there is one nodal circle. If you notice, there is one nodal circle here and there is a diametral line. Okay, so there is one diametral line and one nodal circle. So the plate comes, goes down and has one nodal circle, one crossover again. So this is M1 N1. Okay. Next we have maybe the last one. Okay. So now this is M2. Okay. So as starts, plate starts, place has 1 0 and another 0. So this is m equal to 2 and n equal to 0. Okay. So there are no diametral nodal lines, there are two nodal circles. Okay. There may be one more, let us say. Sorry, this is the same one. This is the same one, sorry. Okay, so these is the nature of the modes. I just wanted to show them animated. Okay, so let us get back to the derivations. The next system we want to discuss is a circular ring. Circular ring. Okay. Now, circular ring, now earlier the beam was a one dimensional structure, right? The cantilever beam with or the simply supported beam, one dimensional structure, one independent coordinate. Now if we bend this, then you get a ring. Okay, so that is also a one dimensional structure. This is also a one dimensional structure. Okay. Now it could have a slight thickness, of course. It has a slight thickness. It's like a ring on the finger. Okay. So what is it effectively? It's effectively a cylinder, a thin cylinder. If we want to describe it in terms of a two-dimensional structure, it's a thin cylinder, okay, whose this length has been shortened. Okay, so that length has been shortened, and all displacements and derivatives in this x direction, if we call that x direction, are 0. Okay, so we can derive or we can obtain equations of a ring, okay, from that of a cylindrical shell, of a cylindrical shell by suppressing ux movement, okay, ux movement and all x derivatives. Okay. Shell is what? Shell is x and theta. X and theta are alpha 1 and alpha 2, alpha 1 and alpha 2. Okay. So, now in order to get equations for a ring which is actually one dimensional, okay, all derivatives with respect to x are suppressed and ux is considered 0. Okay. Then you will get the equations of motion for a circular ring. Okay. So, now I will show you something here. There is a, I will go to the monitor again. Here is the software called Maple, which I was talking about. It is a symbolic software, that means you can use symbols. Okay. So, I have here R1 set as infinity, R2 as x tan alpha, A1, A2 as 1, I mean A1 as 1, A2 as x sine alpha and so forth. So, we can run a symbolic calculation on this. Our institute supports a very old version, but as every year, this year Maple has released their Maple 22 version, and for those interested they are giving a 15-day trial. You can download the software and try it out for 15 days. So, we acquired the software through this 15-day trial advantage. So, now let me show you how it works. Okay. So, I have already programmed the shell parameters for us. You can see conical shell here, spherical shell, toroidal shell, cylinder and so forth. So, let me run it for a plate. Okay, let us this run. So, those are the equations for a rectangular plate. Okay. So, where R1 is infinity, R2 is infinity, A1 is 1, A2 is 1, this is the membrane, this is the bending stiffnesses. Okay. Now, I can do that. If I comment this out, I can do it for a cylinder over here. Okay. You can see I have set the second coordinate to be theta, R1 to be infinite, the radius of the meridian, and R2 the second radius to be R, A1 is 1, A2 is again R. So, if I run it, these are equations at the level of force and force resultants. Okay. This is the equation in the axial direction U1, this is the equation in the theta direction U2, this is the equation in the transverse alpha 3 direction, which is U3. Now, I will shift to the next program, which is for displacement expressions. Okay. So, now here also if I okay, uncomment the first one, uncomment the first and comment everything else, and let us say I run it. Okay. So, now here you have all the three equations. Let me show that. Okay. So, these are the three equations. So, you may remember this is the equation for a plate, a rectangular plate, okay. Fourth derivative with x, fourth derivative with y, and the coupled derivatives E h cube by 12 into 1 minus u square, okay. We change the sign, this inertia term comes onto the same side, okay. And these are the two equations in the x and y directions, okay. So, you can see that in both these equations there is both u2 and u1, that means uy and ux, okay. So, these in plane equations are coupled, okay. So, these are equations at the level of displacements. Now, if I go back up and I comment the top one, which is rectangular plate, and I come here and uncomment this one, and I let us say run it, okay. So, before that let us see, before that, so let us see the cylinder, okay. So, I have set the second coordinate as theta, r1 is infinity, that of the meridian, r2 is r, okay, where the meridian intersects the axis of revolution, then again a1 is 1 and a2 is r. So, this represents a cylinder, okay. So, now if I go down here, these are the three equations. This is the axial equation. To show you just once, let me reduce the size here, okay. So, this is how it looks like. So, this is the axial equation. So, you can see that there is u1 in it, u2 in it and u3 in it. So, it is coupled. Similarly, this is the torsion equation, there is u3, u3, there is u2, there is u2, there is u1 and u3. So, all terms are coupled, and this is the alpha 3 equation. Of course, this is going to be coupled. Now, if we are going to get an equation for a ring out of this, okay, the main course plates and shells has been about 2D structures, okay. Plate is 2 dimensional, shell is 2 dimensional. However, we can get 1 dimensional structure equations also, like a beam, okay, and ring is also a 1 dimensional structure. So, now ring is a kind of a shortened cylinder, okay, the x direction is shortened. So, all derivatives with respect to x we have to shut down, okay, send them to 0. So, let us see, we have here theta derivative, a theta x derivative, so this goes away. Here we have x derivative, this goes away, so these two go away. Then theta derivative survives, then theta x derivative, this goes away and this survives. So, 1, 2 and 3, these are the 3 terms that will survive. 1, so there are 2 terms here actually, 1, 2, 3 and 4 terms that will survive for a ring, and it is a theta equation of motion. Similarly, here this is theta derivative, it survives, this one is x derivative goes away, x derivative goes away, theta survives, x goes away, theta and u3. So, 1, 2, 3 and 4 terms, okay. So, 4 terms here and 4 terms here, these are the 2 equations that are relevant for a ring. Another thing is that once it becomes 1 dimensional, this 1 minus nu square term will not be there, Okay, the beam equation does not have 1 minus nu square. Not only that, for shells and plates it is always force per unit area units. Okay, each term has force per area units, but when you come to one dimensional structures, each term must be force per unit length. Therefore, a width term B has to come in here, the width of the ring or width of the beam. So then this becomes rho A. Okay, and similarly this becomes E, H and B, so EA. Okay, and also for the bending terms where there is h square, okay, there is h square over here, there is h square over here, so this is entire actually bending term. So this will be EBH cube by 12, okay, without the 1 minus nu square. Okay. So now let us look at these equations. Okay. So those equations look like this. D by R4 minus del 3 U3 by del theta cube plus del 2 U2 by del theta square plus EH 1 by R square del 2 U2 by del theta square plus del U3 by del theta is equal to rho H U2 double dot. U2 is U theta, okay, the theta movement in the theta direction. Okay. Then the other one is where D is EH cube by 12. Okay. Then so we can call this or give this the symbol K. Okay. K is EH, we will call this the membrane stiffness. Okay. And the other equation is D by R to the power 4th, sorry, this should be to the power 4th del 3 U2 by del theta cube minus del 4 U3 by del theta 4 minus K by R square del U2 by del theta plus U3 is equal to rho H U3 double dot. This is the U3 equation of motion, U3, okay. This is the U2 equation of motion. Okay. Now just so that I show you a familiar equation that can be arrived from here, if I increase the radius, okay, suppose I increase the radius of this thing, larger and larger values, and you can imagine that somewhere it will start looking straight, very far away from the center it will start looking straight, okay. So or it will start looking straight. So the transverse equation of motion, U3 equation of motion, when it is straight should look like a Euler-Bernoulli beam equation, okay. So suppose R is made to go to infinity. Okay. Now one thing we should remember is that r into d theta should be taken as y, okay, because theta is an angular change and r multiplied by that makes it a linear variable. So r, wherever you have a single r and a d theta combination, you should take it as y. So if we look at this equation, first of all I get d by r cube r del 3 u2 by r cube del theta cube, okay. Okay, let me separate them out. So I get d over r into del 3 u2 by r cube del theta cube minus d by r to the power 4 del 4 u3 by del theta 4 minus k by r del u2 by r del theta plus k minus k by r square u3 is equal to rho h u3 double dot. Now if I take r to infinity, okay, this can be replaced by del 3 u2 by del y cube, but there is still an r outside, so this term goes to 0, whereas here this ends up looking like minus d del 4 u3 by del y4, okay. Again similar, there is r d theta which I can make it y, so this is del u2 by del y, but there is still an r outside, so as r goes to infinity this term goes to 0, this term also goes to 0. So I am left with this term minus rho h u3 double dot is 0 or plus. So this is my Euler-Bernoulli beam equation, okay. So as r goes to infinity, any element starts to look like a straight line, so you get back, okay. If you do a similar analysis over here, this is because this is the theta equation of motion, you will end up with an equation of motion for longitudinal vibrations, of a rod, okay, because as r goes to infinity none of these will survive, this will go to 0, this will go to 0, only the r square and theta square will survive, this goes away. So this is membrane stiffness, second derivative of space and second derivative of time, actually it is the acoustic 1D acoustic wave equation. Okay. So now these are the two, this is one equation and this is the second equation, okay. Now when you have circular elements, okay, when you have circular elements, first of all if you notice all of these are some third order derivative of theta of a certain term, second order derivative of a certain term, again second order derivative of the same term and first order derivative of certain term, okay, is equal to the same term, okay. So and similarly here third order derivative with theta, fourth order derivative with theta, first order derivative with theta, and some term is equal to a same term on the right. So we already know that these are sines and cosines or exponents. Okay. If I differentiate this exponent with respect to x, I get some constant in front and I get it back. Okay. And if I differentiate sine twice, I get back sine. If I differentiate cosine twice, I get back cosine. So already we know that these are the type of terms that are the solutions. Okay. Now we are looking at a ring that is closed. Okay. So if I start somewhere, I go around and I come back over here, the displacement should be same. Okay. So if it is sine some alpha theta, sine alpha theta is, let us say, a solution. This alpha has to be an integer, has to be an integer. Okay. Similarly, if cosine alpha theta is some solution, here also alpha has to be an integer. So let us say we have cos n theta or cos 3 theta. Okay. So cos 3 theta as a solution. Now let us say, where does it go to maximum values, plus or minus 1? Okay. It goes to plus minus 1 when 3 theta is some integer pi. Okay. And this integer can be 0, 1, 2, etc. Okay. Similarly, so where does cos 3 theta go to 0? Okay. So it goes to 0 where 3 theta is equal to, let us say, 2p plus 1 pi by 2, or theta equal to 2p plus 1 pi by 6. Okay. Here theta is k by 3 pi. So now if I look at these values, for k equal to 0, I get a 0. For k equal to 1, I have pi by 3. Okay. For k equal to 2, I have 2 pi by 3. Okay. This is 60 degrees, this is 120 degrees, and if I go to k equal to 3, then it is 2 pi. Okay. So it is 360 degrees. I am sorry, k equal to 3, it is pi, it's 180 degrees. 180 degrees. And so forth. So this is where the maxima are occurring. Similarly, if I set p equal to 0 to look at the minimas, okay, p values going from 0, 1, 2, then what do we get at p equal to 0? I get over here pi by 6, which is 30 degrees. At p equal to 1, I get pi by 2, which is 90 degrees. Okay. Then p equal to 2, I get 5 pi by 6, which is 150 degrees, and p equal to 3, I get 7 pi by 6, which is 210 degrees. So now if I plot it, let us say if I can manage to plot this thing. So this is my nominal ring, this is my nominal ring. and that means undeformed ring, and I partition it now. So these are at 30 degrees, these are at 30 degrees. Now I have a peak here, okay. At 0 degrees I have a peak, okay. Then at 30 degrees I have a 0, so I have a peak and a 0. At 60 degrees I have a peak, that will be a negative peak, okay. Then at 90 I have a 0, okay. Then at 120 I have a peak, okay. And then at 150 I have a 0, so it's a little bit off. 150 I have a 0, okay. Then at 180 I have a peak, 180 I have a peak, okay. And then 1 to 10 I have a 0, okay. Then I have a peak, then I have a 0, I have a peak, I have a 0, I have a peak. So this is cos 3 theta, okay. Now suppose the ring vibrates transversely, okay. The ring vibrates transversely in cos 3 theta mode, okay. So what will happen is that these are 0 displacement points, these are 0 displacement points, okay. So there is some aspect of vibration missing, some vibration information missing, okay. So what I mean is that to complete the information, because any amplitude here is not being represented, okay. If there is a vibration amplitude here, I do not have a representation because it is permanently 0. Same with all these points. Similarly, if there is a 0 displacement point over here, then that is not being represented because this is always at a peak vibration, this is always at a peak vibration, this is always at a peak vibration, okay. And therefore sine 3 theta must also be part of the solution, okay. So you will have two sets of modes, sorry. One with cos n theta and the other with sine n theta. And to represent that they are both are there, okay, that is there is an an with a cos n theta amplitude, I mean variation with an an amplitude, and a bn amplitude with a sine n theta. In order to represent this, what we do is we give it some other a star n cos n theta minus phi, okay. So this carries both information about both the modes now, this carries information about both the modes, okay. Before I close, I wanted to make some statements here. if you recall the ring equation, we had d over r4 some terms plus eh over r square and some terms is equal to rho h u2 double dot. Now our whole derivation with Hamilton's law and so on has been mostly 2D structures, 2D surfaces, and so all terms turn out to be per unit area. If it's force per unit area. If it's mass per unit area. Whereas for Euler-Bernoulli beam, if you remember, it's mass per unit length, okay, rho a. So here also you will have that difference between 1D structure and a 2D surface. All the 2D surfaces will come up with rho h, whereas for 1D it's actually, there is actually a b over here, okay, so that makes it rho a. There is actually a b here which makes this ea, and there is actually b e b h cube, so there is another b over here, okay, which, I mean, if we want we can cancel out, so that we get eh, we get rho h, and we get eh cube by 12. That is the difference between derivation using this method for a 1D structure and a 2D structure, okay. The other important thing is, when I showed you the ring equations, there was 1 minus mu square in the denominator, eh in the maple calculation. So in actuality it will not be there, okay, because I was using a symbolic package that was actually programmed for 2D structures. This 1 minus mu square came, but actually for a ring it will not be there, okay. So the d only in this case, okay, is e h cube by 12, and the k only in this case is eh. I just wanted you to be clear about that. So we will look at the vibrations of a ring in the next class. I'll close it here for now. Thank you.